Good morning. In today's lecture we will see some of the reactions that alcohols undergo, and this will be a theme of both today's lecture and next week's lecture. And we will really see that alcohols are sort of a crossroads of organic chemistry, since many different things can be made from alcohol through judicious choice of reagents. For example, alcohols can be easily transformed by dehydration into alkenes through the reaction with carboxylic acids or their derivatives, such as these chlorides. They can be transformed into esters. This is the reaction known as esterification. They can be reduced to alkanes. They can be reacted with sodium to get the protonic, and then with some other source of alkyl group to give us ethers. Using HX or similar reagents, we can get alkyl halides. And the reactions we'll talk about a lot today will be simple oxidation of alcohol, which gives us carbonyl compounds. And gives us carbonyl compounds of various types. They can be acid, carboxylic acids, ketones, or aldehydes. And so the first reaction we'll cover today will be alcohol oxidation. And in order to do that properly, we would probably need to define oxidation in organic chemistry in the first place. And oxidation in organic chemistry is defined in quite a different fashion from the oxidation in inorganic chemistry. In inorganic chemistry, oxidation reaction is said to be any reaction which increases the oxidation number of a given compound. And so we can go from chromium 3 to chromium 6, or from sulfur 2 minus to sulfur 6 or 4 plus. And these reactions would be oxidations. And conversely, reduction reactions would be those reactions that reduce the oxidation. However, in organic compounds, we're mostly concerned about carbons. We typically have many different carbons in organic compounds with many different oxidation states. And so tracking each individual carbon's oxidation state can become a tricky business. So oxidation in organic chemistry is defined differently. It can be defined as either addition of oxidizing agent, so addition of oxygen or O2 or halides, or simply removal, elimination of reducing agents, such as the most important of which is hydrogen. Alternatively, reduction is defined as either addition of hydrogen or removal of an oxidizing agent. So this could be halogens or oxygen or so. It's also worthwhile mentioning many oxidation reactions, such as protonation or SN2 reaction, SN1 reaction, are neither oxidations or reductions because neither of these two formal transformation is happening. But we will see an example of organic sequence which is an oxidation. We could go from an alkane to an alcohol, and then keep going by establishing another bond with oxygen in an aldehyde, and finally yet another one in carboxylic acid. And so this will be a sequence of oxidations in organic chemistry, which results ultimately in carboxylic acid, which is one of the most oxidized compounds that we encounter in organic chemistry. Alternatively, oxidation would also be a transformation of an alkane into an alkene. Since we lose hydrogen in this reaction, this is also an oxidation. Okay? Now we'll focus more in this lecture on oxidations of alcohols, and we will see that we can oxidize primary and secondary alcohols by a variety of reagents. And we've seen some of them already, such as KMnO4, again manganese in very high oxidation state, nitric acid, even things like household bleach, which are very mild oxidants, can oxidize alcohols. But things that are most commonly used will be chromium 6 plus salts. And these compounds have historically been used quite a lot. They function really well and they're very versatile. but they're being slowly phased out because the chromium-based side products tend to be quite toxic and carcinogenic, and they're a big environmental concern. And so the point is that the primary and secondary alcohols can be readily oxidized, while tertiary alcohols cannot be easily oxidized since there is no hydrogen to be removed on the carbon attached to the OH groups. And so for our purposes, we can say that they are not routinely oxidized. It turns out that they actually can be oxidized if exposed to strong enough oxidizing agent, but that oxidation happens with the cleavage of the carbon chain, and so this is not quite what we desire. So for simplicity purposes, we'll start talking first about the oxidations of secondary alcohols. And these oxidations are typically done with a mixture of sodium dichromate and sulfuric acid, and this will then result in the formation of a ketone, and ketone is the final product of this reaction. This mixture is known as chromium, is a source of chromium 6+, and it's known as chromic acid. Chromic acid is not very stable in its solid form, and this is also, you will sometimes see this referred to as a Jones reagent. Okay? To illustrate this on an example, if we take 3-pentanol and expose it to Jones reagent, we will get 3-pentanone and about 85% yield, so this works quite well. Let's see what happens here mechanistically. The first reaction that occurs is that if we take sulfuric acid and sodium dichromate, we will generate chromic acid, which in its structure actually resembles sulfuric acid quite a bit. We have a central element, chromium, in the 6+ oxidation state. And now this chromic acid will react with our secondary alcohol. And it will react with it in a way which will lead to formation of this chromic ester. Which is shown here. And this is now attacked by a base, which doesn't have to be a very strong base, so water will do. And in a mechanism which sort of resembles E2 reaction, we abstract the proton, form this double bond now between carbon and oxygen, and eliminate chromium as a leaving group, which ultimately results in the formation of a ketone as our oxidation product, as well as this chromium 4 species, which is then further reduced so that the ultimate product is chromium 3 as I said here. And this is how oxidation of secondary alcohols works mechanistically. Oxidation of primary alcohols in its initial stage is very similar. And so we will not going to reproduce this because it's, the mechanism actually is identical. And so we can get from our primary alcohol to an aldehyde in a very straightforward fashion. But then since this reaction is done in the presence of water, aldehyde gets hydrated. And so it adds water. We're not going to concern ourselves with the mechanism just yet. But the point is that we get this geminaldiol. And the geminaldiol is an alcohol, just like any other alcohol, and so this can be oxidized again. And so oxidation of this geminaldiol ultimately gives us carboxylic acid. And so this is the problem of over-oxidation, that even though we wanted maybe to get an aldehyde, we ended up with a carboxylic acid because the aldehyde itself got oxidized. And the problem in this specific reaction is not necessarily the fact that the aldehyde is very easily oxidized. It's the fact that we have water here which then hydrates the aldehyde, giving it a geminaldiol, which is then easily oxidized. And so the solution is to clearly remove water. And so the compound that is used for that is this salt. As you can see, there is no water in this salt. This is the compound known as pyridinium chlorochromate, also known by its abbreviation PCC. And the good thing about this is that it's soluble in organic solvents, so soluble in things like methylene chloride, so it can be easily used in organic solvents, and since it's used in organic solvents, it doesn't require water. And so we can use this for a variety of oxidations, and at that point PCC will make us stop here. So it will stop at the aldehyde stage and will not go any further. So this is the way to get from primary alcohol to aldehyde. Use PCC and methylene chloride. If you want to get from primary alcohol to carboxylic acid, you don't need to be so careful. You can use just Jones reagent in water. Finally, as we mentioned already, tertiary alcohols are not easily oxidized. In addition to chromium-based reagents, we can also use other reagents for oxidations of primary and secondary alcohols. So KMnO4 and nitric acid will inevitably lead for oxidation of primary alcohols to carboxylic acids, but the secondary alcohols will still stop at ketones. However, if you have two concentrated solutions, it often leads to relatively uncontrollable cleavage of these species. One method that recently has been gaining a lot of attention in oxidizing to carbonyl compounds, and this one stops at aldehydes with primary alcohol, is the so-called Swern oxidation. So this oxidation uses some interesting reagents. This is dimethyl sulfoxide. It's a common solvent that you've seen used in SN2 reactions because it's a good polar A product solvent, and then uses this compound known as oxalyl chloride. And once this reaction is done in methylene chloride in the presence of triethylamine, we'll get our carbonyl compound oxidized, and the side products in this case are CO2, HCl, which is typically bound by triethylamine, and dimethyl sulfide. And both of the side products are gases which are easily removed. And so this made this reaction very popular and very clean reaction. The only problem with it is dimethyl sulfide, kind of like thiols, has an unpleasant smell. So this has to be done in a very well-ventilated lab. An example of this Swern oxidation, which is very potent, so it will work at quite low temperature, would be oxidation of this secondary alcohol at minus 60 degrees to a ketone. And so this reaction, because although it gives this product with a fancy smell, none of them are very toxic, and so it's quite quickly beginning to replace some of the chromium-based oxidants as the method of choice for the oxidation. So basically, to summarize this, secondary alcohols are the easiest to control. They just oxidize to ketones pretty much no matter what. Tertiary alcohols cannot be oxidized without cleavage of the chain. And with primary alcohols, you have to be careful not to over-oxidize. If you use oxidizing agents in water, whether chromium-based or potassium permanganate-based, you will go all the way to carboxylic acid. The way to stop that at an aldehyde stage is to use pyridinium chlorochromate, which is an anhydrous source of Cr6+ ions. In the next subtopic, we'll see how these oxidations occur in our body in biological context.